First of all, my name is Dave Ekman with Magnus & Klemenzik Associates. I'm the moderator for this session. And you're sitting in this session, obviously, your rules of thumb for steel design. I'm sure many of you as design engineers have been in meetings with architects and clients, and they want to know how deep that beam needs to be, or how deep that truss is, or how big of a column you're going to need. Well, our speaker today is going to give you some tools to help answer some of those questions. Our speaker is Dr. Socrates Ioannidis, and he's the president and CEO of Structural Affiliates, which is located right here in Nashville. Since he founded the firm in 1986, he's been involved in a myriad of different project types, including industrial, office buildings, healthcare, hotels and housing high-rises, including the hotel that many of us are staying at here, the Renaissance Hotel, which actually happens to be the tallest staggered truss building ever designed. In addition to that, he served on a variety of national and international committees and forums and been published dozens of times on structural engineering topics. He's also been instrumental in bringing steel solutions and steel structures into regions of the world that have typically been dominated by concrete structures, specifically Malaysia and Panama, some of his work. On a personal level, you might also recognize our speaker as an individual that enjoys fine cigars and fine wine, as you see him walking around the conference here. So with that, if you join me in welcoming Socrates to the stage.
Thank you, Dave. I understand our session is being recorded today, so you guys have questions later, and I'll start answering them without repeating your question. Remind me that I have to do that. As Dave said, we're going to talk about some rules of thumb, some shortcut equations that you can quickly make some decisions and check your designs. He mentioned the Renaissance Hotel, and he said it correctly, the tallest design stagger truss, because we have 10 more floors that this building was designed for that were never added to it. As built, was one about less than a year later in Atlantic City that exceeds this by maybe 15 feet or so. It's the Resorts Hotel, but it's still the tallest design. I put this slide here to remind me to give credit to my colleague, John Ruddy. Over the years, I went back, and the first Rules of Thumb presentation was in 1999 in New Orleans at the ASE Structures Congress. I gave the first one, and then we keep kicking the ball back and forth and adding things to it. John is going through some hard times right now with his health, so all of you that know him and those that don't, have a prayer for him. Okay, how many in here know what this is? This is the slide rule. Not so long ago, when we were asked to design, we would develop some kind of analytic model. We would confirm that it was appropriate, prepare some sort of calculations. Yes, we use pencil, paper, slide rule, whatever. You do a graph check on the order of magnitude. Decimal accuracy says in there. This always reminds me of a poster that a 91-year-old engineer that worked for me until the day he died, he had in his office that said, he showed a bridge floating down the river, and at the bottom he said, the engineer was watching the bridge go down the river, and he said, there goes my decimal point. Because when you use slide rules, you get the significant figures, but you have to figure out where to put the decimal. So then we verified that the results were reasonable, and then we would check it with some rules of thumb. Nowadays, and I'm not talking about hundreds of years ago. I'm saying this was like 20 years ago or 10 years ago. Now what do? We get on the computer, we build a model, and then there is a button called Design. You hit that Design button, voila, it's done. And we walk away. He said, man, we designed this building in a few seconds. So why do we need rules of thumb now, since we have this wonderful software? Well, first of all, to make some on-the-spot intelligent decisions, to get some preliminary, even the best computer programs, you still have to give some input to it. So to figure out what your input is, where you start from. Sometimes doing structural design is a self-fulfilling prophecy. You hone in into what you want the answer to be, and you keep running it until you get the answer you want. At least you have a way to make sure that you're shooting for the right answer, and to validate the results of computer programs. These rules of thumb came from different places. They've been collected from peers. After the session yesterday, a lot of people came up to me and said, did you know about this rule of thumb? Did you know about that rule of thumb? So somebody astutely saw that I was changing my presentation here at the end. I said, all I'm asking you is if you do have some rules of thumb to fit in, and by definition a rule of thumb is something that's easy to apply and hopefully easy to remember, then send it to me. This has been a developing, evolving presentation, so maybe the next time you hear this presentation, your rule of thumb might be in it. Also, sometimes you just look at things and say, I wonder if this works. And sometimes you derive it. You say, I don't want to have this difficult equation. Can I figure out a better way to do it? Of course, these are approximations, and they're not always conservative. And you have to, verify it by more comprehensive analysis. Finally, the rules of thumb are based on a allowable stress design, because they were developed long before LRFD. During the years when AISC was pushing LRFD and LRFD only, we got a lot of pressure to change these to LRFD, and I started trying to do that, and my numbers instead of 5 and 3.5 ended up being 6.8, and then I wanted to make that a 7, and it didn't work. So we resisted it long enough until in 2005, and thanks to Mr. Jim Fisher over here, we now have LRFD and ASD together. So therefore, there is no reason. And after all, these are rules of thumb. You have your loads, you know them already. There's no reason to multiply them by load factors and so forth. You use the loads as they are. And since you never go into what is actually the allowable or the ultimate stress, it's all built into the rule. So you start with your raw loads and you apply them, and that's it. A very basic relationship is the area-weight relationship, and it comes, of course, from the density of steel. And if you work out all the units and the fact that weight is pounds per foot, just like we normally call an 18 by 35 is 35 pounds per foot, and the area, of course, is in square inches. And by applying the density of steel equation, you find out that the area of any steel shape is simply the weight over 3.4. So if you know the designation, if it's a 18 by 40, then you know that the area is 11 point something inches. Let's look at some approximations then based on that. Typical I shape, if we say that is composed of 2 T-sections, and the center of gravity of each T-section is approximately 0.4 d away, then the moment of inertia is 2 times the area of the T times the d 0.4 d squared. You go through all of this and you approximate that the moment of inertia of any I-beam is d squared times the weight over 2. Okay, so you already have in your grasp, you know what the size of the member is, and you're trying to find out quickly what the moment of inertia is. You know the weight, you know the depth is 18 by 35, so this is 18 squared times 35 divided by 20. And here is a comparison of the actual moment of inertia to this approximation for the economy sections in the AISC table. It should be obvious now that we can very easily find the section modulus. This is the elastic section modulus that we use with allowable stresses. Okay, and that's simply the depth times the weight over 10. Okay, and here is the relationship, the comparison rather. The radius of gyration about the strong axis, and this one took some, more graphical. This is one of those derived things. Okay, we got to figure out what this is, and we plotted the actual shapes along the x-axis and the rx along the y, and try to see if we can fit something to it. And here is what it looked like. So if you say that the moment of inertia about the x-axis is approximately 45% of d, you will be conservative in most cases, up to 22% conservative, and in some cases on the heaviest sections of each column category you will be slightly unconservative. But if you're designing a 14 by 730, hopefully you do more than rules of thumb to figure out. This is a very interesting one, and this is relatively easy to derive actually if you think about it, because all your moment of inertia is essentially two rectangular sections that make up the flanges, but it's approximately 25% of the width of the flange. Okay, so far I've been dealing with depth and weight that you always know, right? So now all of a sudden, we have the width of the flange. If you're designing long enough, you probably have a fair idea about where you are. But if you don't, this trusty card that you're going to get at the end of this, and I promise you, I think I have enough for everybody today. So this actually has some column sections and the width of the flanges listed on there. And again, here is a relationship, the comparison. Okay, this is actually what started this whole rules of thumb presentation. Long before John Ruddy and I worked together, we became friends through a committee, ASC Committee on the Design of Steel Building Structures. And about the second meeting we had, that was probably in 1974, Jim, somewhere, or 73, somewhere there. He pulled me over to the side after my martini and his scotch, He said, Socrates, you look like you're a young whippersnapper. He said, I see you doing good with that computer. Back in those days, there was no laptops, but there were transportables. So I would actually carry a box that would not work on battery. You have to plug it in, but at least you had it with you where you went. I said, you have the thing with you, and I see you on there while you're in the meeting. I see you designing frames and all this stuff. I said, do you know that if you take the moment in a beam, you multiply it by 5 and divide by the depth of the beam, that will give you the weight? I said, no way. There cannot be anything that simple that works. Well, let's see. To finish the story, I went back from the meeting. It was usually we had a Friday meeting, so I came back. Actually, I lost my flight in Atlanta because I was in the crown room. There you go. I was in the crown room trying to program the whole steel shape using Fortran. There was no Excel and all of these things, and I went and I got so involved I missed my flight. I worked a little bit longer. This is a true story. I went in the wrong plane. And I went to the plane that my last flight was leaving from. And it was before 9/11 and all of this, so they didn't check your boarding passes very well or anything. And as I'm walking on the plane, I said to the stewardess, that's what you call them back then, so don't call me racist or whatever. So I said, this plane is going to Nashville, right? And she said something, and I understand what she said. We get on there, they close the doors, and they announce we're going to New York. And I said, hey, I said, hey, I asked you. He said, yeah, and I told you I will give you a parachute to fly. I didn't hear what she answered. I was so involved in developing 5M/D. So anyway, I actually ended up in New York. I had to come to Nashville the next day. All because of John Ruddy and 5M/D. So if we start with the using 36 KSI material, the allowable bending stress is 24 KSI. You go through the equation and you see is weight times D over 5 is the moment. Or if usually you know the moment to start with, so the moment times 5 divided by D. Now John put a different slide in here. When I give this again, I'm going to have the other slide as well, where I developed it back way when, where you put every steel shape that is in the steel book, and then you put this equation on. But this also gives it just has the economy sections on here, so you can see that it's a conservative approximation, and the heavier the moment, the further away you get, but it's always on the conservative side. And it's an easy number to remember. I mean, we could have probably made it 5.2 and the line is closer, but you want something that you can easily remember. Okay, if you're using 50 KSI steel, you just ratio that to 36 over 50, so you can see that should have been 3.6. But again, we'll try to make it simple, 3.5 M over D. And here's the relationship again. Okay, when you have composite beams, you usually end up with 70 to 75% of the weight of what you would have needed to use if it was non-composite. So we simply use 70 to 75% of the moment and apply the same 5 M over D or 3.5 over M over D. Here's something else. A lot of times erectors and fabricators, want to know how many studs do you have in here. They like to hear them in studs per square foot, or in some of the parts of the world I work with is how many studs per square meter. And if you're ending up with more than 3 studs per square meter, something is wrong with your design. So, and sometimes they start telling me, oh, we figure 10. I say, oh, no. So anyway, but here is a good approximation. We're using mostly 3/4 inch studs, of course. The number of shear studs is approximately equal to the weight, 1.1 times the weight. Of course, you have to turn it into a round number because you have to have them equally spaced if you have uniform load. Now, this is using AISD design. It's an interesting phenomenon. When we went to LRFD, what we found out early, and what sold LRFD to most engineers in the first place, is that you came up with approximately 1 size smaller for composite beams than what you used to do in ASD, just by looking at the ultimate. But interestingly enough, the number of studs required to develop the same moment was essentially the same. But since now you're using a lower weight, if you try to do this relationship back to the weight, you end up saying that the number of studs is approximately 1.25 times the weight. So before you had an 18 by 40 times 1.1, that would be 44 studs. Now it's an 18 by 35 times 1.25, exactly 44 studs again. Okay? So LRFT does not give you more studs. It gives you the same number of studs, but you end up with less weight on your beam, so the relationship is different. Let's look at the beam example. Let's say we have a 32-foot span, and we want to use an 18-inch beam. We're using 36 KSI material, and we have 1 kip per linear foot. A trusty WO square over 8. I didn't put that one on the card, by the way. I assume all of you remember that one. So 128 foot kips. So the weight needs to be 5 times 128 divided by 18, 35.56. So depending on whether you're Socrates or John Ruddy, you would end up with an 18 by 30 or 18 by 40. So again, it's an approximation, so you say, okay, we're going to use an 18 by 40. If you look at the capacity, it's actually 135. You see, I would have used an 18 by 35 and then I would have come back and make this check here and realize it wasn't enough, and then had to use an 18 by 40 anyway. Okay, here's the same span. We're now using 50 KSI, and we're limited to a 16-inch depth. Go through the numbers. You say, I need a weight of 28 pounds per foot. We know there's no such an animal as 16 by 28, so we try a 16 by 31, and it's right on the money. Trusses. If we look at the chords of the trusses, the compression side usually will govern with an allowable stress of 22 KSI. This is just from experience. The equivalent depth is approximately 9/10 of the total depth of the truss. Therefore, the force in the cord. Now, in this whole presentation, the units are the conventional units that we use. So all of the conversions for units have been included in the equations. So your moment is always in foot cubes, the depth is always in inches, the weight is in pounds per foot, and so on and so forth. So you can see here the first thing we do is convert the moment into foot cube inches and divide by this. So we end up that the force in the cord is 13 times the moment divided by D. Therefore, the area of the cord, since we have 22 KSI, is 0.6 M over D. And the weight of the cord, truss strip 3.4 again, that we talked about, gives you approximately that the weight of the cord is 2 times the moment divided by the depth. What is it? Okay. This is purely from, my experience. Approximately, if you already know what the weight of your cord is, the total truss is going to weigh 3 times that weight. Essentially, you have 2 cords, and all the webs, if they're designed in some logical fashion, end up being 1 more time. So you multiply that. So for a truss then, using 36 KSI material, the weight is 6 times the moment divided by the depth. Or if we're using higher strength material, 4.5, again rounding these numbers to where they make sense. Let's talk a little bit about columns. This is the column curve with KL over R on the bottom and the allowable stress on the top. We try to strike a simple straight line through it. Again, this is rules of thumb. Ted Galambos was in here, he would kill me. But so a very simple equation fits that curve, and that is that the allowable stress is in essence 22 minus 0.1 KL over R. And if we're using 50 KSI material, that modification factor becomes 0.15. Okay, let's check a column. Say we have a 12 by 58. The width of the flange is 10 inches. And again, you don't need a steel book, huh? You have the card. That will tell you it's 10 inches. Allowable stress 50 KL is 18. Well, we have to make, no, this one we know. Okay, so therefore the radius of gyration is 2.5 inches. You go through it, therefore and since it is at 21 by 58, the area is 17.06. We go through and we find that the allowable axial load is 291 kips. If you compare that to the code equations, that's 302. Okay, let's talk a little bit about structural depths. This is one usually we're in meetings and the mechanical engineers are screaming. They need to put these bigger ducts and they want to know exactly how deep your members are. For roofs and roof joists, essentially half the length. The length in feet, the depth in inches, okay? So if you have 30-foot span, you need a 15-inch member. For floor beams and joists, it's 0.6, and if those happen to be composite, it's somewhere in between. But I tell you, I just simply remember a ½ inch per foot is a good place to start with, even though we can be a little bit higher. You know, so you do that and you add a little bit, you're okay. And it depends how much you want to give to the rest of the design team in that first meeting. You do this calculation in your head and you find out it needs to be 16 inches, but you may say, I need a 21-inch beam right here. So that you can give it to them later and they feel good. Because then they forgot that that 16-inch beam needs fireproofing on it and there's all these other things. So it depends, you know, when you first start, you always have, what do we call them? Not fudge factors. What did I call them, John? Well, the 1.2, what did I call it? The uncertainty factor. You have uncertainty factors. So you can do your best analysis that you can at that time, even if it's analyzing a 52-story building and you come up with how many pounds per square foot, because you don't know what you don't know at that time. So you put a factor when you give it, and then as the process goes, as you learn more, as you feel more comfortable, the factor becomes less and less. In the end, it becomes 1. Okay? This is like for industrial applications, cantilever, continuous roof systems. Of course, the hinge or splice location is somewhere 15 to 25% of the span. And for cantilever or continuous roof beams, it is more economical to run the beams in the short direction and the joist in the long direction, and the optimum bay size is around 30 by 40. On the other hand, if you're using joist and truss joist systems, you run the girders in the long direction, and the optimum bay is 40 by 40, which of course has no long and short, but if you ended up with anything else, is that still correct? And the advantage of the first system with the beams and joists is that you end up with essentially a uniform thickness system. The advantage of the truss girders, of course, is a total package, but you end up with the heavier members on the long. But because they are open web, it is not such a big problem, because even if you need to run services, you can run them through the webs. Aspect ratio of tall buildings. The aspect ratio of a building is usually always reported as the width of the building or the height of the building divided by the width. But in reality, if you had the system like the one shown on the first sketch there, and assuming that those connections beyond the truss panels are not moment connected, then the width is only the width of that braced element. The typical range of H over W is 4 to 9, with an efficient system around 5 or less than 5. There have been projects reported in the 10 to 12 range, and staying true to the saying that if it sounds crazy enough and nobody else can do it, call Socrates. We have a project now that is 1,150 feet tall, and it's only 20 feet wide. So that's about a 20 to 1, 19 to 1. We figured it out, but we ended up having to put another tower next to it of the same dimensions and tie them together. This is a direct extract from late Fazlur Khan, who, of course, you know, if it came from him, it was written 30 years ago, so there's some adjustments to this, but I copied it verbatim to give him credit. He said if it's less than 30 stories, you know, you can usually use rigid frames. Nowadays, you know, actually a braced frame or a combination of the two is used quite a bit. 30 to 40, you definitely need to do some sort of interaction with shear elements. He's calling it frame shear wall, but the shear wall or a brace frame, I give you the same thing. If it's 41 to 60, you need to have some additional help with maybe some belt trusses and outriggers. If it's 61 to 80, you need frame troops, and if it's 81 to 100, it's a truss tube with interior columns, and if it's more than that, it's bundle tubes. This is Sears in Chicago. Okay, how does the steel get distributed in a high-rise building? The floor framing doesn't change. The gravity, whether it's on the first floor, on the 100th floor, is the same. The columns are essentially going through a linear transformation because as you put, as you go higher, you put more load on it relative to the height. And it shouldn't surprise you that the lateral load resisting system is exponential because the loads are of the same shape. This actually came from Fazlur also, although no credit is given to him here. But I did not hear it from him. The first time I heard it was from Build a Measure. But when I did some research, I found out that it came from Fazlur. But if you wanted to find out how many pounds per square foot you have in a project, in a high-rise project, you take the number of stories divided by 3 and add 7. Now this is assuming some sort of a normal system. Nowadays, I don't remember the last time we designed a purely steel frame. It's usually some sort of composite. So you take this number and adjust it based on your experience of a composite column, what percent is that of a non-composite column, and so on and so forth. Sometimes you need to know you're in a meeting and they also ask you how long before the steel is done. And you can tell this slide is outdated. We need Mike Engstrom in here to tell us what the real delivery time is, but it's not 8 to 10 weeks anymore from the notice to proceed. It's more like 14 or 20. Depends whether you buy your steel, from a service center or from the mill. But this is an interesting average. Everybody asks me, how many crews do you have? This is an average of what you get. 80 to 160 ton per week is what you can erect. If you talk to an erector, they say, okay, how many pieces do I have? What is the weight of the typical piece? What does the connection look like? But we polled a few of them and we kind of threw a number in here. So let's say we have a 12-story building, 360,000 square feet. And of course we know how much it's going to weigh, right? It's 12 over 3 plus 7 pounds per square foot. You multiply that, you have about 2,000 tons. And say it takes 10 weeks from the notice to proceed. And it takes 16 weeks to erect by using the average of those numbers. So therefore it would take 6 months. A lot of you that have white or gray hair probably still remember this. Those of you with black hair probably know a different number because you use it in an ultimate. But the fillet weld capacity is a little bit less than 1 kip per 16th of an inch of the weld size per inch length. Another simple fact, but often ignored, and I had a whole paper about this about 10 years ago to prove that this is the case, and several others have followed since then, is that the deflection of a simple beam is usually 80% of what you calculate because of the connections providing some rotational capacity, even simple bolted connections. Fire resistance ratings. If you're in a meeting, again, the architect usually looks at you, they didn't used to ask us this question, but ever since W.R. Grace has been going around and teaching everybody that steel structures are unrestrained, now they decided, oh, we don't want to take on this responsibility. So they actually ask you nowadays. Thank you very much, Dave. So these are some of the usual UL numbers, that we use typically in the hospital and office construction. For composite floors, it's either 902 or 925, 916, whether you're using Isolatec or Grace. Okay, so now you're in a meeting. It's at the beginning of the project, and somebody wants to know, hey, what's the depth of my structure? The architect wants to know what is the column size, because he's going to design that wrap around that column exactly, since we're building a watch. And you're sitting there and you're scratching your head. Or what is the estimated tonnage? Can we change the depth of this beam from 24 to 18? At this point, your colleague who's sitting at the other side of the table, she's scratching her head. And you say, is it better to use W12 or W14s? And, you're being put on the spot. You hardly know about the project. You just walked in, you saw the drawings on the conference table, and they're looking at you now. You're it. So what do? You use the card, which I promise you're all going to get one today, not like yesterday. Okay, and this card is actually, we use this. This is our index card that we carry around, except on the back we have all these rules of thumb. And it looks something like this. First of all, in the center you have your economy section beams, in case you don't remember them, and a few more. And then on the very left you have the columns grouped by flange width, so that you can use that RY that we talked about. And then you have the equations that we're describing here. Anytime you see a shaded equation, that means, and I'll show it boxed in here, that means it's for Fy equals 50. Okay? So it's very simple. Let's do a rough design of a column. How many in here have ever done a calculation for a column that started with a picture that looked like this? Okay? A few of us. Okay, this is the way we used to do columns. You just have to write it down, find out what the tributary area is, multiply it out, put your load, and then carry it all the way down, and now you know what your load is in every floor. So we have a total of 140 pounds per square foot. We're actually going to design we'll have a 30 by 30 bay, 5 1/4 inch lightweight concrete slab with 2-inch deck, and we're using 50 KSI material, and we want to do composite design. So for the beams, the uniform load is 1.4 kips per foot. The moment is 158. 3.5 times 70%. Okay, that 70% is because we're using composite. Divided by 16, it says it's a 16 by 24. Therefore, let's use a 16 by 26. Maybe it needs to be a 16 by 31. For a girder, we don't even bother to try to put the point load on, just put it in as a uniform load. But we do have a reduced load now. You see 115 because the girder takes a lot more load. And the moment is 388. Therefore, if we use a 21-inch member, it would say 45 pounds per foot, whether it's a 21 by 44 or a 21 by 50. 21 by 50, you use just 5 pounds more per foot as long as the depth is allowed. You have increased your deflection control by more than 25%. So as usually, for me, when I'm designing, I would make the jump. Interior column, we have full live load reduction as we go down. So we end up with 81 kips on the roof, 99 on every floor, ending up with 480 kips. We use 50 KSI. The allowable is this trusty equation we have, but now we don't even know what our R is because we don't know what column we're starting with. So let's just assume that the slenderness reduces the allowable stress by 10 KSI. In other words, that 0.15 times KL over R is about 10, which says that we have an allowable stress of 20. We do a trial weight, and we ended up with 81 pounds per foot. So let's try a W12 by 87. Now we can calculate the RY is 3 inches, or we can estimate it, and in reality it's 3.01 if you check it out in the book. The KL over R is 60. Therefore, the reduction is 9 KSI versus the 10 that we have assumed. And we see that this can carry a lot more load than what we need. It's now 537 kips. And if we check this actually based on the allowable, based on the column curve, we get 588. On columns, you're always going to be conservative on the lower KL over R's and a little bit less conservative. You remember how the approximation fit the column curve. So let's try a 12 by 79. Notice that for a 12 by 87 and 79, we estimate the same RY because we said it's 0.25 of the flange width. But in reality, there is a slight difference. It was 301 before, it's 305 now. So now we see that we can carry 487, or if we actually checked it out rigorously, it's 531. So we're going to use a 12 by 79. Well, there was actually a RAM model done, not only of one bay, there was more to it, but I think we isolated one just to look at it. And here are the results. 16 by 31 for the beams, 21 by 50 for the girders, and the interior column was 12 by 79. Again, we might want to consider changing that one to a 24 by 55. Now, we sit here and we say, okay, we have all of these computer programs and we can design buildings and so forth. And then when rules were tools, what happened back then? We had the pyramids without computers. We had the Parthenon. I had to put the Parthenon in there. You know, the Washington Monument. And poor Eiffel, Gustav Eiffel, was almost exercised, you know, for building this tower. But it's definitely an indication of what engineering can be. Okay, and please, after watching this presentation, if some of your own rules of thumb came to mind, send them to me, and they might show up in the next rules of thumb presentation. Thank you very much.